Hello, today I'd like to talk about determinants. The motivation behind determinants is that we want a function that tells us how much space is stretched or squished by a linear transformation, which is a matrix, and for the determinant to make any sense, we need it to be a square matrix. You'll see why in a sec. In a trivial but good for intuition case, n equals 1, our space that we're stretching or squishing is just the real number line, and our matrix is just a 1 by 1 matrix of x, which is a real number. We're working with multiplication here, so m1 acts on the multiplicative identity by just having the matrix x act on 1, x times 1, which is x, so m1 stretches 1 from itself to x. We can extend that via linearity to basically say that since this is a line and things are linearly and stretched nicely, for any other number y, we're also stretching it by a factor of x, so the determinant of m is x. In the n equals 2 case, things get a little bit more interesting. M2 goes from R2 to itself, stretching or squishing it somehow. It is a 2 by 2 matrix with real values A, B, C, and D. Let's give those column vectors a name, U and V. And again, look at the identity matrix of 1, 0, 0, 1, column vectors I and J. And M2 acts on I via multiplication, which just takes those columns to be exactly M. So I gets taken to U, J gets taken to V. Now for some pictures. So right here I have our R2 vector space. I is right here and J is right here, determining a unit square of area 1. And since it has area 1, we'll just call the determinant of I 1. And this linear transformation of M is taking I to U, moving space linearly with it, and similarly J to V, moving and squishing space linearly with it. And so this unit square gets taken to be this parallelogram, and the amount that is stretched or squished is exactly the area of that parallelogram. And because everything's moving linearly, we know that any area in this space will actually get stretched or squished by the same factor that that area is. And you can figure out the formula for that using this picture right here. So homework, find that formula. And yeah, so let's talk about what happens when we vary U and V a little bit. So if U gets really big, we're stretching space even more. If U is very small, comparison to those unit vectors, we're squishing space more. And let's say what happens when U gets closer and closer and closer to V, the parallelogram gets squished and squished and squished until when U is on top of V, they're linearly dependent, gets all squished onto just one line, with that parallelogram having area 0. So when you have linearly dependent column vectors, the determinant will be 0, and it turns out that that works backwards as well. If U is counterclockwise to V, we move past squishing all of space onto one line. That'll like flip space, and so the determinant captures that by being negative whenever U is counterclockwise to V. That's all I'll say about the degree 2 case. For the degree 3 case, our linear transformation will be determined by 3 column vectors. We'll have a unit cube of volume 1, and those 3 column vectors of our linear transformation will determine a parallelepiped of some volume, and that volume is exactly the determinant of that linear transformation of R3. And there's a nice recursive pattern for figuring out the formula there. Thank you very much for listening, and have an awesome day.